We will do now some exercises. So the first one, let G from R to R be continuous and increasing. For AB in P, define mu G of AB equals GB minus GA. So this is a non-negative quantity because G is an increasing function. Then there exists a unique complete measure mu G bar on a sigma algebra containing all the Borel sets and extending mu G. So this is called the Lebesgue-Stieltjes measure. Okay, so solution. So exactly as in the case Gx equals x, in which case you get the Lebesgue measure. Okay, so because then mu G is then nothing but B minus A. Okay, in exactly as in the case Gx equals x, there exists, we have a measure on R extending mu G. So if E belongs to R, then E equals union I k equals 1 to n ik in P and disjoint. Then you define mu G of E. There's only one way to define this, is sigma k equals 1 to n mu G of ik. Once you do this, then the Carathéodory method gives mu G bar. So you go to the hereditary sigma algebra ring generated by it, which is, it will turn out to be again the power set because you are dealing only with P and R again, and therefore, and then you will get the mu star measurable sets, which will give you a complete measure. And we know from the abstract theory that it contains R and therefore the sigma algebra generated by R, namely all the Borel sets. So this completes the proof of this. 2. Let S1 contained in R2 be the unit circle. Show that there exists a Borel measure on S1. S1 is a topological space because it inherits the topology of R2, and therefore you have open sets, and the sigma algebra generated by those open sets are called the Borel sets in S1. So there exists a Borel measure on S1 such that mu of S1 equal to 1 and mu is invariant under rotations. Solution. So you take T from 0 to pi to S1. So T of theta equals e power I theta, and that gives you a point, or cos theta I sin theta if you prefer the real coordinates, and therefore you will get a mapping here. Okay, and this is a bijection. So if you define S to be equal to set of all E contained in 0 to pi such that TE is Borel. Okay, so obviously empty set and 0 to pi belong to S, and S is a sigma algebra because this is a bijection, so it's closed under complementation and of course under the union. So this is a sigma algebra. Now if U contained in 0 to pi is open, so there will be two possibilities. U could be contained in the open interval 0 to pi, and this implies T of U is also open in S1. Okay, by the mapping here. And then if you can also have U is something like 0 alpha. Okay, then T of U is nothing but the point 1 union T of 0 alpha, and this is Borel again, and therefore all open sets, so implies Borel sets contained in S. So similarly for T inverse. Therefore E Borel if and only if T Borel. Now you define mu of, so now you take E in S1, and then you define mu of E is 1 by 2 pi of M1 of T inverse. Then of course mu of S1 equal to 1, and mu is a measure on S1. Now we want to show that rotation invariance. Okay, so you have, let T theta naught equals rotation of S1 by an angle theta naught. So you take the circle and you rotate it, you get back the circle again, and so you have this. Now what is T theta naught? Of E? This is nothing but T of theta naught plus T inverse of E. Okay, where T is the mapping which I gave before, and therefore this, and therefore M mu of T theta naught of E is equal to 1 by 2 pi of mu of theta naught plus T inverse of E by definition. And because, so this is not mu, this is M1, and M1 is translation invariant, and therefore this is equal to 1 by 2 pi of mu M1 of T inverse of E, which is equal to mu of E, and therefore it is invariant under rotations. 3. A. Consider the triangle with vertices 0, 0, 1, 0 and 0, 1. Call this triangle T, and therefore compute M2 of T. So we know what it is, because we know that essentially it is area, but we have to prove that, and therefore we have, it's half base into height, so the answer should be half. We know this, so let us try to show it exactly. So solution. So this is the triangle T. This is 0, 0, this is 1, 0, this is 0, 1, and of course this is 1, 1. Okay. Now you look at A from R2 to R2 given by A of xy equal to 1 comma 1 plus 0 minus 1 minus 1 0 xy. I am writing just a reflection along this line. What I have written here is nothing but the reflection along this diagonal here. So then you have a0 0 equals 1 1, a of 0 1 is here you get minus 1 plus 1, that will give you 0, and 1 will give you 0 1 will give you minus 1 1, sorry, this will give you 1 0, and this will give you so it's just a reflection of these two. So if you call this triangle T dash, then the M2 of T dash is nothing but, by translation invariance, this 1 1 doesn't matter. So modulus of determinant of 0 minus 1 minus 1 0 times M2 of T, okay, is equal to M2 of T. And then this single line is a one-dimensional thing, so you know its measure is 0, and therefore we have M2 of the square 0 1 cross 0 1, which is 1, is equal to M2 of T plus M2 of T dash equals 2 times M2 of T. So this implies that M2 of T equal to 1/2. So this is a formal proof of this. Okay, so next, B, T triangle with vertices xi yi, I equals 1 2 3. Show that M2 of T is equal to 1/2 of mod determinant of A, where A is the matrix 1 1 1 x1 x2 x3 y1 y2 y3. So this formula you would have been taught when you did analytic geometry. Given the three vertices, how to find the area of the triangle. So we are going to formally prove this formula here. Again we use the same trick as the previous exercise part. So we define T of A of xy equals x1 y1 plus x2 minus x1 x3 minus x1 y2 minus y1 y3 minus y1 xy. Okay, then 0 0 gets mapped to x1 y1, and then 1 comma 0 will get mapped to x2 y2, and then 0 comma 1 will get mapped to x3 y3. So M2 of T is nothing but modulus of the determinant of x2 minus x1 x3 minus x1 y2 minus y1 y3 minus y1 times M2 of the times half, because that's the into half, because that's the area of the triangle 0 1 1 0 0 1, and therefore this but what is this? Now if you look at the determinant of 1 1 1 and then x1 x2 x3 y1 y2 y3, this is nothing but 1 x1 y1 0 x2 minus x1 y2 minus y1 0 x3 minus x1 y3 minus y1, and therefore hence the result. So this proves this. For compute M2 of S1. So you have S1 is a unit circle, and then we want to compute its Lebesgue measure in this. So now you take S1 is nothing but the intersection of k equals 1 to infinity, or okay, doesn't matter. So you take epsilon k tending to 0. Okay, so then you have set of all xy. Okay, so you have that x square plus y square less than or equal to 1 plus epsilon k, okay, minus x square xy, since x square plus y square is less than or equal to 1 minus epsilon k. So you take the unit circle and then you take a circle of slightly smaller radius and slightly bigger radius, and then you remove this, and therefore it is intersection of all these. Okay, and therefore that is equal to, now you have a set of decreasing sequences, series sets, and then the intersection is S1. So this is nothing but limit as k tends to infinity of M2 of set of all xy such that x square plus y square is less than or equal to 1 plus epsilon k minus M2 set of all xy x square plus y square less than or equal to 1 minus epsilon k. Okay, so now you can show that this is equal to limit k tending to infinity omega 2, so I'll tell you what omega 2 is, into r square, so 1 plus epsilon k minus omega 2 into 1 minus epsilon k, and that is of course 0, where omega 2 equals m2 of S1, B1, where B1 equals unit ball, and we know of course that this is equal to pi. This is in the assignment. You can prove this, that if you're given the measure of the unit ball, then the measure of the ball of radius r is nothing but omega 2 times r square. Okay, so this is what we. Then 5. Let A from Rn to Rn be non-singular, linear transformation. E contained in Rn show that mu star of E equal to mod determinant of A, mu star of A. Then deduce that Lebesgue measurable if and only if AE is Lebesgue measurable. We did this only for Borel sets earlier, and now we can use this thing to show that. So let solution E be contained in union Ik, k equals 1 to infinity, and Ik belonging to P. So this is how, so mu star of, so AE is contained in union k equals 1 to infinity mu star of Ik. Okay, so mu star of AE by subadditivity, this is less than or equal to sigma k equals 1 to infinity mu star of Ik, which is equal to mod determinant of A. We know this, sigma k equals 1 to infinity mu, sorry, A of Ik, A of Ik, mu star of Ik. So take inf over all possible covers. So you get mu star of AE, this is still a lower bound, less than or equal to mod determinant of A, and then inf of sigma mu star of Ik, and that is equal to mod determinant of A mu star of E. Okay. Now A inverse is also a non-singular thing. So mu star of E, E is nothing but A inverse of AE. So this is less than or equal to mod determinant of A inverse mu star of AE. Sorry, let me write it differently. A inverse of E this is mu star of E, which is A inverse of AE, so that is less than or equal to mod determinant of A inverse of mu star of AE. Therefore, mu star of AE is greater or equal to mu star of mod determinant of A inverse mu star of E power minus 1. Okay, that was the problem. Okay, so now we have power minus 1, which is equal to determinant of A mu star of E. I bring this to this side, so I get, so I have now both inequalities, less than or equal to, greater or equal to, and therefore this implies that mu star of AE equals mod determinant of A mu star of E. Okay, so now it is now straightforward for the Lebesgue measurability. So let us take E Lebesgue measurable and F contained in Rn. So let us take mu star of F intersection AE plus mu star of F intersection AE complement is equal to mu star of A inverse F intersection E plus mu star of A inverse F intersection E complement. And that we know is mod determinant of A times mu star of A inverse F intersection E plus mu star of A inverse F intersection E complement. And that, since E is Lebesgue measurable, so this is nothing but mu star of A inverse of F, which is equal to mod determinant of A inverse into mu star of F, and these two multiply equal to 1, and therefore you get that AE Lebesgue measurable. So now similarly apply to A inverse for converse. So if you have two measures on a given sigma algebra, mu1, mu2, we say that mu1 is absolutely continuous with respect to mu2, and you write mu1, this is the notation, if mu2 of E equal to 0 implies mu1 of E is 0. Okay. So let T from R to R be a bijection such that T and T inverse map Lebesgue measurable sets to Lebesgue measurable sets. Define mu of E is M1 of T of E. Show that mu is absolutely continuous with respect to the Lebesgue measure. So solution. So M1 of E is 0. To show mu2 of E is 0, that is M1 of TE is 0. If not, M1 of TE will be strictly positive. Then we know that there exists F non-measurable, F contained in T of E. This implies T inverse of F is contained in E, but mu M1 of E is 0 and Lebesgue measure is complete, and therefore this implies T inverse F measurable implies F measurable, because T of T inverse F has to be measurable, and that's a contradiction, and therefore you have that M1 of T is 0, and therefore you have absolute continuity. Okay, so we will stop with this, and next time we will start measurable functions.